Good afternoon, all of you. Today, I, Naveen Garg from BSc Chemistry Honors final year. I am going to read a chapter for visually impaired students from the book Pradeep, Physical Chemistry, Volume 3, Dr. K.S. Kheterpal. Chapter is Molecular Spectroscopy and Section Electronic Spectra. Section 3.51 Introduction. It has been discussed in the last chapter that we have a molecules absorbs energy in a microwave region, far infrared region. Transition between the rotational levels takes place given in a rotational spectra. Similarly, if the energy is absorbed in a near infrared region, transitions takes place between a vibrational levels accompanied by the rotational level given vibrational rotation spectra. However, if a light is absorbed in a visible region or ultraviolet region, the electronic transitions takes place given electronic spectra. A number of other processes also takes place for the absorption of a light called photo process. These may be a photophysical process such as fluorescence, phosphorescence, photochemical reactions. The branch of science which deals with such purpose is known as photochemistry. It is the present chapter we shall take up a brief study of electronic spectra, whereas photochemistry will discuss in a later chapters. Electronic transitions and band spectra. Theory. Section 3.521. Theory of electronic bands and spectra. Just as there are electronic energy levels in atoms, there are electronic energy levels in molecules also. However, there are no simple formula available for energy of electronic levels except for hydrogen-like atoms. Electronic spectra are obtained when an electron is in a molecules are excited from a lower electronic energy level to the higher energy level. However, as the electronic transitions is accompanied by a vibrational and a rotational transitions, the total energy of a molecule in any state is the sum of the electronic energy, vibrational levels and rotational levels. If E of E, E of nu and E of R represents electronic energy, vibrational energy and rotational energy respectively of a molecule in initial state before transition, and E of dash, E nu of dash and E of R of dash, the corresponding values of a final state after transitions, then we have energy of a molecule in the initial state. Total E is equals to E of E plus E of V plus E of R. Energy of a molecule in a final state is equals to E dash of E plus E mu E V of E dash plus E dash of R. Equation number 2. Therefore, the energy change involved in an electronic transition will be given by delta E is equals to E dash minus E. So, that is delta E is equals to delta E of E plus delta E of V plus delta E of R. Equation number 3. But according to the Planck's quantum theory, delta E is equals to h nu, that is equals to h nu hc nu bar. hc nu bar is equals to delta E of E plus delta E of V plus delta E of R. So mu bar is equals to delta E of E plus delta E of V plus delta E of R upon hc. Equation number 4. As for a particular electronic transition, so that delta E remains constant, and for a particular vibrational transition, so the delta V remains constant. As delta E of R can have a different value due to the different rotational transition within the same vibrational energy change of same energy electronic energy levels. A number of closely spaced lines are obtained. This constitutes a band. For a vibrational transitions, a separate band will be obtained. Thus, due to the different vibrational transition of a particular electronic transition, a set of band is called band group or a band system. Each electronic transition will give a band system and hence a complete electronic spectra involving a different electronic transitions gives rise to a series of band groups. Thus, the electronic band spectra obtained for a gaseous molecule is quite complex. In spite of a molecule complex nature of a electronic band spectra, they are preferred over the other types of because of they are obtained in a visible and ultraviolet region, so that these can be easily photographed and studied. Calculation of a dissociation energy of a molecule. A study of electronic band spectra reveals that at one end of of the spectra, the distance of a separation between the lines becomes smaller and smaller till ultimately the line spectra vanishes and space of a continuous emission starts. The frequency corresponds to the point where the line spectra vanish in a frequency necessary for a dissociation of a molecule into atoms. Thus, electronic band spectra can be used not only for getting the information as given by vibrational rotation spectra, but it can also be used in evaluating the dissociation energy of a molecule. Section 3.53, the potential energy curve and the Frank-Condon principle. The explanation of electronic spectra band and the dissociation energy can be earlierly understood in the terms of potential energy curve and the Franklin-Condon principles as follows. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of a system versus internuclear distance between the two approaching atoms. The curve obtained is of a slope given in a figure 3.38. However, even at a minimum energy position, the equilibrium position represented by point x, the atoms are vibrating so that the internuclear distance keeps on changing. Therefore, the potential energy keeps on oscillating about a minimum position. The vibrational levels thus occupied by a system may be represented by a horizontal line and indicated by an appropriate vibrational quantum number. If a sufficient energy is supplied to the system occupies the vibrational level represents mu d dash infinity, that is the molecules should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electrons jumps to the higher energy level, that is electronic transitions takes place and dissociation will takes place only of a molecule in a higher energy level. Now, every electronic state has on its own potential energy curve. Two such curves of a lower electronic states are shown by figure number 3.39 by 1 and 2 respectively. They differ in the fact that the minimum of a potential curves for a excited state 2 is at a larger internuclear distance than a ground state energy electronic states. The dissociation energy for a two states are different as shown in a figure. D2 less than D1. This is evidently due to the fact that the bonding in the excited state is weaker than in the ground state. The vertical distance between a minima of a two curves gives the difference between the electronic energy of a two states. The transition between a two electronic states takes place according to Frank-Condon principle as explained below. According to the Frank-Condon principle, the nuclei being much more massive than the electron and the electronic transitions takes place more faster than that of a nuclei can oscillate to change their internuclear distance. And in electronic transitions takes place for a extreme end of a vibrational level. Example for A dash shown in a figure 3.39. Because of a velocity of a vibrational energy of an atom is zero at these positions, they spend maximum time at these points. As internuclear separations remains the same, the transitions can be represented by a vertical line from a point A dash to the point C of a upper curve and not for a potential energy minimum of a lower curve to the upper curve, the new vibrational level. The new vibrational level must be one which is nearest to the point C. Continuing the level, it appears that excited molecule will be the third or a fourth energy level, state 2. This explains why the electronic transitions therefore is a simple selection rule for a transition among the vibrational levels. All type of transitions for the lowest vibrational level of maybe of any of a vibrational level or a higher electronic states are possible. It may be mentioned that here that according to the quantum mechanics there are transitions from a lowest level mu 0 is equals to 0 takes place from a midpoint of a midpoint of a vibrational level, which is the equilibrium or the most probable position, and not for the extreme positions. Each vibrational level has a large number of very close space rotational levels, which are being shown in a diagram. Now, when the transactions takes place for a vibrational levels of a lower electronic states of some vibrational levels of upper electronic states, it is accompanied by a number of transactions between the rotational levels. The result is a group of a closely spaced lines or called branches. Since a number of vibrational transactions takes place, a group of bands called band system is obtained. Further, as a transaction takes place between a many different electronic states, the result is the electronic band spectra consist of several band systems. If electronic transition similar to A-C takes place, the results in an absorption spectrum consisting of a number of vibrational bands. If however, a transition similar to BD takes place where point D represents the vibrational level correspond to the internuclear distance in the infinite, the molecule dissociates. Thus, when such a transition takes place, the absorption spectrum consisting of a number of bands corresponds to the transition from a ground state to the definite vibrational level in the upper states. But these are the bands will coverage the finally passing into a continuous region of a continuum when which has no fine structure. The point at which the continuum start is called convergence limit. The frequency and hence the energy correspond to this limit gives a dissociation energy of a molecule. However, it is important to note that after dissociation, atoms are produced in an electronically excited state and not in a ground state. Hence, to obtain the energy of a dissociation into ground state, the excitation energy of atoms must be subtracted. Lastly, it may be pointed out that if a minimum of the upper electronic state is nearly at a same internuclear distance as of the ground electronic state, the transition from mu is equals to 0 of a ground state to the mu is equals to 0 of a upper state is strongest. Section 3.54 Electronic spectra of a diatomic molecule. As shown in a figure number 3.39, in case of a diatomic molecule, when a photon is absorbed by a molecule, the most probable electronic transitions takes place accordingly to the Frank-Compton principle. If from mu is equals to 0 at a lower electronic state, mu is equals to 2 of a higher electronic state, this is called 0 to 2 transition. Other transition from mu is equals to 0 level of a ground state electronic state to a different vibrational level of excited electronic state also takes place, but with much lower probabilities. Thus, the transition from 0 to 2 has a maximum intensity, whereas other transitions have a smaller intensity. The result is a spectra of a type of shown in figure number 3.40. Section 3.55 Selection rules for electronic transitions in a molecule. In order to understand selection rules for electronic transition in a molecule, we should first understand a few terms in a symbols to be used in there. First is parity. 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 Parity represents the behavior of a orbital which represents with respect to inversion. It is used for a molecular orbitals of a homonuclear diatomic molecules. We consider a point in a molecular orbital and not of a sign of a orbital wave function. Then we travel equal distance through the center of a molecule of a point, center of inversion. On the other hand, the operation is called inversion. If at this point the orbitals have a same sign, it is said to be have an even parity and denoted by G from a Girardet. And if orbitals has a opposite sign, that it is of a odd parity, it means denoted by U, that is ungirardet, uneven. The parity designations applies only to the homonuclear diatomic molecule, because heteronuclear diatomic molecules like HCl do not have a center of inversion as shown in a figure written by mu and Girard, and a bonding pi orbitals have a odd parity and have a pi mu, and pi star orbitals have a parity that is denoted by pi Girard. The parity of orbitals is even, symbols is G if inversions through a center of symmetry. A sign of orbitals remains same. If a sign changes, parity is odd and the symbol is U. That is Angirade. The second point is multiplicity of a state. The ground state or excited electronic state of any species may be have a one or more unpaired electron with the spin in the same direction or opposite direction. If S dash represents the total spin, the quantum number, then 2s plus 1 gives the spin multiplicity of a state. If S is equals to 0, the multiplicity of a state is 1. If S is called a singlet state, it is called a single state. If S is equals to 1 by 2, then multiplicity is equals to 2. It is a doublet state. If S is equals to 1, then the multiplicity is 3. It is called a triplet state, and so on. For example, in the ground state, H2 positive has only a 1 electron. It has a multiplicity 2. Similarly, O2 molecule in ground state has a 2 unpaired electron with a parallel spin. Then its multiplicity is 3. Point number 3, that is term symbols of a molecule. These molecules gives a complete information about the state of a molecule and the orbital angular quantum number, angular momentum, multiplicity and parity. Depending upon the components of a total angular momentum above the internuclear axis, there are gives a symbols summation, multiplication, delta as follows. The component of a total angular orbital angular momentum about the internuclear axis, that is 0, plus minus 1, plus minus 2, and so on into h ki power h upon 2 pi. The symbol for 0 is summation, for plus minus 1 is pi, plus minus 2 is delta. To above symbols, the multiplicity is added on the left as a superscript and a parity is added as a script on the right. For example, first, if the single electron in H2 plus is sigma molecular orbital, has a 0 orbital angular momentum, and hence the symbol term is symbol term is sigma. Symbol term is summation. Further, if the multiplicity is 2 explained earlier, then parity of only occupied by a Girard G star, and therefore full term symbol is 2 summation G dash. If the term symbols for any closed shell homonuclear diatomic molecule is 1 sigma G, because the spin is 0, as all these electrons are paired, then there are no orbital angular momentum from a closed shell or of a overall parity is a G. If there is only a pi electrons outside a closed shell, its orbital momentum is of internuclear axis is equals to 1 unit. Hence the term symbol is pi. If there are 2 pi electrons as in O2, the term symbols may be of sigma or a pi. The term symbol summation will be used if the electrons are orbiting in opposite direction, which can be if occupies different orbitals. The term symbol pi will be used if 2 pi electrons orbiting in the same direction, which can be if they are occupies the same pi orbital. In case of O2, in the ground state, the 2 pi electrons occupies the different orbitals with a parallel spin, and the overall parity of a molecule is equals to closed shell is Girard into Girard, that is G. Hence the term symbol is used is 3 summation G. Lastly, a superscript plus or a minus or a on a summation term symbol is added to show the behavior of a molecule wave function of a reflection in a plane containing the nuclei. In case of O2, the one electron is it of 2 pi x, which changes the signs of reflection in yz plane, and other in a 2y dash, which does not. The overall reflection symmetry is therefore closed shell into plus into minus, that is equals to minus. Hence the full terms symbol is 3 summation g negative. Now we give the below selection rule for our transitions between different states of molecule. First is the only the transactions are allowed between the states of which are difference in a component of a orbital momentum along a z-axis 0 plus minus 1, and thus summation minus summation, pi minus summation, and delta minus pi transactions are allowed, but delta minus summation is not allowed. Second is the transactions are allowed only between the states have a same multiplicity. Thus the singlet state and the triplet transactions occurs may be allowed. The singlet to triplet transactions are not allowed or forbidden. Third is sigma positive to sigma positive and sigma negative to sigma negative transactions are allowed, but sigma positive to sigma negatives are forbidden. Point 4. Only those transactions are allowed which are accompanied by a change in a parity. Thus, Girard to Ungirard or Ungirard to Girard are allowed, but Girard to Girard or Ungirard to Ungirard are forbidden. This is known as a Laporte selection rule. Section 3.56 Molecular orbitals sigma, pi, and eta involved in electronic transitions. The most common molecular orbitals present in a molecules are bonding molecular orbital sigma and pi correspond to the anti-bonding molecular orbital sigma star and pi star. Besides, these may be of a heteroatom N or O present in a molecule. Then they have an orbital containing a lone pair of electron. As that of a non-bonding electron pairs, there are designating by the N, that is non-bonding orbitals, and they do not have any corresponding anti-orbitals. In case of a homonuclear diatomic molecule such as H2, N2, etc., the highest occupied molecular orbital is HOMO. In a ground state is a bonding molecular orbital BMO, whereas the lowest unoccupied molecular orbital LUMO, lowest unoccupied molecular orbital in a anti-bonding molecular orbital ABMO. The electronic transitions takes place from HOMO to LUMO on absorption of a suitable energy, usually the shortest wavelength part of a ultraviolet region. The transition may also take place for n orbital to the antibonding molecular orbital. In the other words, the electronics may be excited from a sigma, pi or n orbital to the sigma star and pi star orbitals. Thus, transitions which are allowed from sigma to sigma star, pi to pi star, and n to pi star or n to sigma star read as sigma to sigma star, pi to pi star, and n to pi star transactions. The type of transactions involves depending on the nature of a component and takes place by the absorption of a frequency characteristics of a compound or a group present. Taking an example of a carbonyl compound, that is aldehyde or a ketone example, the sigma, pi and n orbitals are their excited state are shown in a figure number 3.42. Thus the transactions takes place are n to n star for at a wavelength of 280 nanometer and pi to pi star at a wavelength of 180 nanometer. Further, it is interesting to point out that if a single electron excited for a of exciting and antibonding molecular orbitals has a spin opposite to the electron left in a lower orbital. The total spin of an excited state is s equals to 0, so that the multiplicity is equals to 2s plus 1, that is equals to 1. Hence there are an excited molecule will be of a singlet state. If two electrons in the upper and the lower orbitals have a parallel spin, s is equals to 1, so that 2s plus 1 is equals to 3, excited state is a triplet state. The excited state are classified as a singlet or a triplet. A triplet state has a lower energy than that of a singlet in accordance with the Hund's rule. As already explained, O2 is in a ground state, is in a triplet state. It shows that exceptional behavior as that of electronic transitions takes from a triplet ground state to the triplet excited state instead of a singlet excited state. That is why the spectra of O2 molecule is quite complex. The type of a transitions which certain categories of a compound undergoes and region of a wavelength absorbed by the transitions are given below. Saturated hydrocarbons or compounds containing C2C or C2H single covalent bond requires very large energy to produce electronic excitations, usually beyond 160 nanometers far in the ultraviolet region. In such molecules, sigma to sigma star transitions takes place. Point second. A simple olefin has an absorption band about 170 nanometer. In such molecules, pi to pi star transitions takes place. Third is molecules like methylamine and methyl iodide, which do not contain pi orbitals, undergoes n to sigma star transitions. Point 4. All electronic transitions in organic compound do not occur in ultraviolet region. The occurrence of a colored compound indicates the absorption of radiation in a visible region. The compound containing N double bond N group or a long conjugated system double or a single bond, including aromatic ring, absorb at a wavelength of greater than 180 nanometer. That is why looked color. Such groups are called chromophores. In such cases, the energy of a molecule's orbitals lies close to other and pi to pi star transitions takes place. Example of a protein beta carotene has a fairly long conjugated system and absorbs light for about 240 to 280 nanometer. Intensity of electronic bands. The intensity of an electronic band depends on the extent of overlapping between a wave function of a ground state and the excited state. Greater the overlapping, greater is the intensity, as there is a very poor overlapping of a wave function in n to pi star transition, and there is an excellent overlap in a pi to pi star transition. The intensity of a band produced by n to pi star transition is very low as compared to the produce of pi to pi star transition. Further, in the presence of an acid, the electrons of n orbitals undergoes promotion and the n to pi star band disappears.